Well guys, let's have a look at constant acceleration today. This is the second in our series of our kinematics extravaganza, and it's very, very interesting. So without any further ado, let's have a look. Now, if A, the acceleration, is a constant, then we get a whole series of beautiful formulae that we can use to analyse the motion. Now, let dv dt equal A, which is in this case a constant. If A is a constant, you have full license to use the formulae which I will show you how to derive here. And you will need to use these formulae very, very regularly when you have constant acceleration scenarios, okay? Now, I've just anti-diffed that from dv dt equals A. If you take the antiderivative of that, you will get v equals at plus c, and that's the constant of integration. Now, if the initial velocity is u, that is at time 0, then we sub that in as a boundary condition. So v equals u when t equals 0, we get that. Okay, and therefore c equals u, doesn't it? Therefore, we can say that, and this is the first of our Academy Award winners of constant acceleration motion, v, the final velocity, equals u, the initial velocity, plus a, the acceleration, which is a constant, times t. Don't ever use these formulae unless the acceleration is constant, because you will be wrong. That is the first of our formulae, which will become near and dear to your heart as time progresses. Okay, that's number one. Now, if we then go another step and we integrate that one to get displacement, okay, that's v is really dx dt, isn't it? Okay, and it equals u plus at, which we've just found. We integrate that again, we'll get, okay, x, this is the displacement now, is ut, that's the antiderivative of that, plus a half at squared, which is the antiderivative of this one, plus another constant of integration, which we'll call d. Okay, now if x happens to be 0 when t is 0, that means that d will be 0. And what do we get? We get the second of our Academy Award winners in the constant acceleration stakes here. Okay, marvellous, isn't it? Now let's change direction here. We're going to eliminate time by using these two equations. So from equation 1, we can say that t equals v minus u divided by a, okay? And what we're going to do is we're going to substitute that into number 2, and we're going to get a mess. But it will become clear and easier to work with as we simplify it. So therefore you can say that x equals u times, this is what t is. Okay, have a look, see if you agree. There's t. Plus a half a times t all squared. Now that's going to take a little bit of simplification, but it's alright, it works out beautifully in the end. So we're going to solve this to find v in terms of u, a and x, and there won't be any t anywhere, because that comes in very handy not to have t in some scenarios given to us for constant acceleration. So here we go. Let's trudge through the algebra mud. Now, does that make sense? Let me see. Ah, yes, it does, because that's there's the 2 from the half there, and this is going to be a squared, and which is partially cancelled out by this a here, just leaving 2a on the denominator. Okay, now I think we better multiply both sides by 2a to get rid of these pesky denominators, don't you? And let's see what we get. Oh, very, very exciting. So what do we get? 2ax equals 2u, I get that, yes, times v minus u, plus this thing over here without the 2a. Okay, very good. Now if we multiply those brackets out, good heavens, I told you, a bit of a mess. 2ax equals 2uv minus 2u squared plus the expansion of this quadratic. Okay, v squared minus 2vu plus u squared. Now look at that, that's going to cancel out with that. And what else is going to happen? Anything else? Oh yes, this minus 2u squared and the plus u squared. So it all comes out like in the wash, and we get that. And that is our third formula, which we use for constant acceleration. That one's got no time in it, okay? All the other two do have time. So that's the third Academy Award winner. Okay, you've got to know those formulas like the back of your hand, guys. Don't rely on a formula sheet. Know them. Okay, they become part of your psyche. Okay, but only use them for constant acceleration. Do not use them in any other situation. You have to be told you've got uniform acceleration before you have a license to drive with these formulae. Okay, now the fourth one, which you'll sometimes use, is that the average velocity times the time gives you the displacement. Now, to me, this is fairly intuitive, but I'll explain it to you in a way that you'll always get it from now on, hopefully. The average velocity, if you've got constant acceleration, it'll just be u plus v over 2, because I'll show you on a graph. See, if you've got, starting with u, initial velocity of u, final velocity of v, over a time span t, okay, then the average of those 2 points on a number, on a line there, right, you know, it's like the midpoint. The average is the midpoint, isn't it? Which is just going to be u plus v over 2. That's your average, right? Now, it just so happens, guys, that the displacement, I'm jumping ahead a little bit here into the next video, but just suffice it to say to you that the displacement is equal to the velocity times the time. So the displacement will also be the average velocity times the time, as I've showed you in this scenario here, where you're going up with a constant acceleration. That means there'll be a constant gradient on that line. Now, the area under the graph is what I'm getting around to telling you. The area under the graph, in other words, v average times t, gets you the area under that graph, and that is the displacement. That is the displacement in that situation. Now, I'll put the formula down, then I'll show you on a better graph why that is so. So u plus v over 2, or that midpoint there, or the average velocity, which equates to this red line here. This average velocity times the time is the area under that graph, that rectangular graph there made up by that flat line there, v average, times the time. Okay, so length times width of this rectangle gets you the area under the graph, which is the displacement. It is the displacement, okay? And it actually applies to any velocity time graph. The area under that graph, no matter what the shape is going to be the displacement, okay? It is. But for this particular scenario, it's very easy to work out. It's just basically the average, which is this one here, u plus v over 2. Okay. Now, if I haven't confused you, we'll just continue, and I'll show you here, and you'll get it a lot easier. Now, if I was to have a scenario here with a velocity time graph here, velocity here, time here. Now, if we were doing, say, as an example, 50 meters per second for 10 seconds, right? You think about that. 50 meters per second for 10 seconds, what would be your displacement? It would be this times this, which would get you 500 meters, right? So that's that area. The area under that graph happens to be this velocity times this time, length by width, gets the area under the graph. It also happens to get you the displacement, okay? Just by logic from using this formula here. So now you're beginning to see that the area under the graph of a velocity time graph is the displacement. Now, here's a different scenario for you. Watch this. If I was to start off at 30 meters per second here and finish at 70 meters per second, the average of those two velocities, the starting at 30 and the finishing at 70, would be 50, because it's halfway in between. It's the midpoint of this line. Okay? Now, what I'm putting to you is that the average, the area under this graph here, this trapezium graph with the orange bit up here, is still the same. Is still the same as what the area under the graph with the green flat line here, as our V line here would be. So the displacement would be the same in both scenarios. The displacement would be the same in both scenarios. E.g., whatever the formula for the area of a trapezium is, it's the average of this height at 70 plus this height at 30 times the 10, divided by, add up those heights divided by 2, then times the 10 would be the displacement, because it's the area under a velocity time graph. but that's also equal to the area under this graph here with the green line here, constant at this value of 50. So 50 times 10 is 500. Now, I'll show you why that is. You have a look at that. If I take this line, this little triangle here, if I make a hinge there, just like that, right? Now I'm going to swivel this little triangle over, swivel it over, rotate it around, swivel it over, and plonk it into there. Watch. Here it goes. Now, you see I've just created exactly the same area as we were considering for the average velocity as what we had in the trapezoidal situation there, with the starting at 30 and the finishing at 70. So I hope I've demonstrated to you that the area under a velocity time graph with constant acceleration is basically the area under the graph is achieved by just taking the average velocity and multiplying it by the time. You get the same area, hence the same displacement. And that's what this formula is. Now, I know, it's a mind-boggler, isn't it? So, we're armed with that information. You've got this formula here. You've got this formula here for displacement in terms of time. You've got this one here with velocity, displacement, acceleration, velocity, it's final, initial, acceleration and displacement with no time anywhere, and you've got this one here. Okay? Average velocity times time gives displacement. Now, we're going to use some real life examples. Yes, there's the final graph there after I rotated the little triangle around on itself, and I got to there. Yeah. Now, here's an example which we should do. Okay? Alright, we've got a body moving in a straight line with a uniform acceleration. Now, that gives us our license to use these formulae, okay? But if they don't say that, you haven't got any right to use these formulae. I can't emphasize that strongly enough. And it's got an initial velocity of 12 meters per second. After 5 meters, velocity is 20. Find the acceleration, alright? And then the distance traveled in this time, and the time taken to travel a distance of 200 meters. Okay, that's pretty straightforward. Number A, we've got to get the acceleration. Now, we know that U is 12. I usually write all these variables down. V is 20, T is 5, and A is don't know. We've got to find A. So from that, from the information that you do know and the information that you have to find out, you decide which of those formulae you're going to use. And in this case, it would be that one. Okay? So we plug all our values in now, we get that. Have a look, see if you agree. Yes, and therefore, we're saying 8 is 5A, therefore A is 8 over 5 meters per second per second. Okay, that's A done and dusted. Now we want the distance travelled in this time. Okay, that'll be the displacement. Because A is constant, therefore, and A is 8 over 5, therefore, displacement will be the same as distance in this scenario. There's no change of direction happening here. Now, what do we got? We want to know, oh yes, we've got that. The displacement equals x equals ut plus half at squared. Now we happen to know a now, and we happen to know t, don't we? Yes, and we happen to know u, because that was 12. And yes, very, very good. And that was over 5 seconds, all right? So therefore we've got that to plug in, and we just have to clean that up, and we've got x. Looks like 80 meters. Okay, we travelled 80 meters in that 5 seconds. Right, part C, the time taken to travel a distance of 200 meters. Okay, so this time we're going to put our x in there as 200, here, this little baby, and we know our u and we know our a, and we're going to work out what t is. It looks like it'll be some sort of quadratic. Better multiply by 5. Yes, very good. Now we can divide through by 4. Now we've got to solve that thing. Goodness. I just thought of it. 250 is 25 times 10, and I can get 15 out of 25 and 10, can't I? So I think that's the answer to it. Yes, look at that. T plus 25 times t minus 10. Now, when you solve that by the null factor law, you're going to get t is 10 or t is minus 25. Now this little beastie here doesn't make any sense at all in the context of time, although it's mathematically okay in the context of the question we're dealing with here, where time has to be 0 or positive. That makes no sense. So it looks like t was 10. There you go. There you go. T is 10. That's it, isn't it? We've done it, have we? Good gracious me, we did it. Okay, easy peasy, easy peasy. Thank you very much. Now, another one. A body is moving in a straight line with uniform acceleration at an initial velocity. See, there's your license to drive. Uniform acceleration, right? Okay, with an initial velocity of 12 meters per second, all right? The body stops after 20. If the body stops after 20 meters, find the acceleration of the body, okay? Now, you've got to basically interpret the question. This is saying that V is 0 when x is 20, all right? This is u. That's u. V is 0 and x is 20. How are you going to find a? I think I know. I've just twigged. Write down your variables. U is 12, x is 20, v is 0, and a is what? That's what we've got to find out. I think there's no... Do you notice there's no time mentioned anywhere there? I think, therefore, it's a case for this one, this formula here. And we can just plug and play now. There it is. And we can work out, by solving that, yes, that step's right. And we can basically then take the 144 over the other side as minus 144, then divide both sides by 40. And we get that, which we can cancel through as minus... how exciting. Minus 3.6. meters per second per second. Alright, that's the acceleration. Put a box around that. And it's hooray today. Yes, yay. We did it, didn't we? It's excellent. Now, we've got a stone being thrown vertically upwards from the top of a cliff. Okay, one of these vertical ones here. A vertical one. We've got a cliff which is 25 meters high. Okay, the velocity of projection of the stone is 22 meters per second. Find the time it takes to reach the base of the cliff, and you give your answer to 2 decimal places. This is the case where you've got to decide which direction is positive, up or down. So what I've chosen to do here is always draw a little picture. I usually choose up as positive, okay? And then if you're consistent with whatever your choice is, the thing will work out perfectly fine within the context of whichever direction you've chosen as being positive. But you just have to be consistent with that in the way the thing unfolds for you, and what you call plus and what you call minus. Okay, now, there's my scenario. I want to work out the time it takes to do this. Like that, bang. Okay, it was a stone. So there you get a stone's throw, yes? A stone's throw. Our answer is a stone's throw away. So let's go with this now. I'm saying that u was plus 22 meters per second, and I'm saying that a, therefore, is going to be minus 9.8 meters per second squared, yeah? So x is, the final resting place is minus 25, because that, to me, in my frame of reference, I'm choosing that as being x is 0, okay? That's where we started off. It's going to finish down here. You don't have to do the journey in 2 bits where it goes up and then goes down. The whole thing is taken care of in the maths. Even the turning around and coming back down, the whole thing. It's so beautiful, isn't it? Maths is incredible, the way it works. So there we go. Now what we've got to do is work out t, okay? Looks like x equals ut plus a half a squared to me, sticking out a mile, don't you think? Yes? So let that put a smile on your dial as we go through this little exercise. And now what do we know? That's minus 25, that's plus 22, this is the unknown, that's minus 9.8 in my frame of reference, right? So put it in, and there we go. Now we've got this fairly awful looking quadratic, and I think that's why they asked us to do it to 2 decimal places. We just have to reach for the calculator for that, I think. Solve it with the quadratic solution or on CAS. Oh, wow. Look at that. So what do we got? I've used x because I'm used to using x on the CAS. So solve this thing here. This is with the TI CAS handheld, which we use at my school. That's the syntax that you would use. And we get this. Most interesting. So this negative value, remembering that this is really time, that would have no meaning whatever in the context of the situation we're dealing with. Therefore, this has got to be our answer. Therefore, to 2 decimal places, I'm saying it's 5.43 seconds. Da-da-da-da! Varshy B, guys. And you're a star. And huzzah! So these are really, really fun, these formulas, and they're really gimme marks in exams if you know what to do. But you never, ever, ever, ever use them unless you have a license to drive, which means they tell you that the acceleration is uniform, or in this case, we know the acceleration is uniform because we've got gravity, okay? Gravity, which is always a constant force, and therefore it produces a constant acceleration down towards the centre of the Earth, which is at 9.8 metres per second squared. Alright, I won't rabbit on anymore. I hope you had a good time doing that. Go and do some practice. Have a wonderful time. And I'll see you in the next exciting instalment, which is going to be velocity time graphs. Okay, bye-bye.